I'll be talking about 2D Yang-Mills. This is based on one work with S.Smith and R.Zhu. They're both in Beijing now. The message of this talk is actually very simple. Basically, in Yang-Mills theory, so Yang-Mills theory has an interdimensional symmetry called a gauge symmetry. So when we talk about correlations in this theory, we care about correlations of gauge invariant observables, observables which are invariant under the symmetry. So these observables are called Wilson loops. On lattice of any dimension, these Wilson loops are well defined, and also in continuum dimensions 2, they are also well defined. What's interesting is that these Wilson loops satisfy a sort of recursive relations, which are called Makeenko-Migdal equations. These are also called, under many names. They're also called master loop equations, or Dyson-Schwinger equations, or just integration by parts. So basically, these recursions are type of integration by parts for Yang-Mills. So these Makeenko-Migdal equations, they are known to hold on lattice of any dimension, and also in continuum in 2 dimensions. And in a recent paper we posted earlier this year, we proved that in 2 dimensions, these Makeenko-Migdal equations on the lattice converge to the Makeenko-Migdal equations in continuum. Okay, so it's very simple to state our result. But I guess the point here is this convergence is in a proper sense. So maybe in the talk I'll clarify what would mean, in what sense they converge. But I'll first spend 20 minutes or so to review what are these equations. So let's start from the model. Lattice Yang-Mills model, so we have a lattice and the spin variables are defined on the edges, on the bounds. So given a bound xy, the spin variable called qxy take value in the Lie group, for example, un. So qxy, for example, is a unitary matrix. And then field is just this collection of unitary matrices over all the edges. Now, there's an energy or action functional for this field, for this Q field. What this energy does, it basically measures how flat this field configuration is. By being flat, I just mean if you take any plaquette P, right, x, y, z, w, then multiply the 4 matrices along the 4 edges. If the product is just identity, then we say it's flat here. So now this energy measures how far this product is from the identity. So the distance, I measure this distance between the identity and the product by a real part of the trace. There are other ways to measure this distance, for example, this is called a Wilson model, but there are also the Lamb model and so on. Basically, you measure this distance with the heat kernel and so on. And then I sum over all the plaquettes. That's the energy of this configuration. So now we can make it random, right? So the probability that you can get this field is proportional to e to the s, or beta inverse temperature. So this dq is the Haar measure, basically the analog of the big measure on the Lie group. So the gauge symmetry I mentioned earlier means the following. If I take any function g, which lives on the vertices x or y, so also take value in the Lie group, then I use the g to do a gauge transformation on this field q, right? So multiply the q on the left by gx, on the right by gy inverse. You can check this energy is invariant. Okay. So this is a huge symmetry because g is a function. Of course, the Yang-Mills model was first defined by Yang-Mills in continuum, and the lattice model was defined later. Lattice model was defined to discretize the continuum Yang-Mills model so that it preserves the gauge symmetry. But the continuum Yang-Mills model was defined first, and the field here is a one form, so it has d components. Its analog here is you have d directions of the edges. Like here you have d components. And each component AI is a function taking value in the Lie algebra of that Lie group. So if that Lie group is UN, then the Lie algebra is a matrix of the school's permission matrices. So, and the energy functional for such a field A is the so-called L2, or the so-called curvature. The curvature is a two-form, and the ij component is equal to this curl-like linear part, plus a nonlinear term, which is a Lie bracket of Aij, basically the matrix commutator of Aij. And now the formal measure is again given by exponential of this energy, so times the formal Levy measure. On finite lattice, this measure is completely well defined, but this is a formal measure. Okay. There's also a gauge transformation, which leaves this energy invariant. So any question about definition? Maybe a question is how are these two related, right? So in what sense this is the right discretization of the continuum model? Well, the relation of the Q field and the A field is the following. So you should think of Q as exponential A, right? A take value in the Lie algebra, so exponential A is the group. And here the epsilon is a lattice spacing. So basically, when you pass from lattice to continuum, when epsilon go to 0, this epsilon A, basically what happens is that Q is closer and closer to the identity of the Lie group, so that essentially you're around the identity, so you should look at the Lie algebra element. You can actually check on the energy level, if you substitute Q by e to the epsilon A, then you have product of 4 exponentials, and there's something called the Baker-Kimball-Hausdorff formula, which tells you how to approximate that. Then you can see that indeed, as epsilon go to 0, this energy SQ will go to SA. Okay, so on the classical level, this is true. But this doesn't mean that the measure, the discrete measure also converges to the continuum measure. Okay. And when you do that calculation on the energy level, it's very easy to see that beta should scale like epsilon to the d minus 4. Okay, so what is the Wilson loop? On the lattice, it's defined as follows. Take any loop, it's a red loop here, I multiply all the Q variables, the matrices along the loop. So this product over the loop of QXY, and then take the trace. So this is actually a number, given any loop, give you a number. And what's special here is this number is gauge invariant, which is very easy to check, right? So the gauge transformation is defined like this. And if you just sort of insert the G and the G inverse into this definition, into this product, they are all cancelled. Okay. So in continuum, the Wilson loop is defined in terms of holonomy. So, in geometry, the field A is a so-called connection in the fiber bundle. And for connection, you can talk about holonomy. It's a non-abelian version of line integral, if you want, line integral 1,4. So how is it defined? So if gamma is a loop in RD, the holonomy, okay, so the Wilson loop observable for this loop gamma is defined to be the trace of the holonomy along this loop, back to the origin, back to the starting point. So how is this holonomy H defined? Well, we parameterize this gamma by S, and then we solve this ODE. So here, H take value in the Lie group, and A is the Lie algebra value 1,4, and D gamma is a tangent vector. So this is a pairing between 1,4 and the tangent vector. So this gives you sort of infinitesimal integral of this 1,4 A. So since A take value in the Lie algebra, this pairing gives you a sort of Lie algebra element. And if you solve sort of dH equal to H times something, you sort of exponentiate this infinitesimal thing. into the Lie group. So you get a solution, you get sort of curve H, which is curve in the Lie group. Now this curve starts from identity, and when you come back to the starting point, the H1 is some other element in the Lie group, and take the trace of that. Okay, so in some sense, maybe one way to, if the first time you see this, if you ignore the H on the right hand side, then the H should be just line integral of A along the gamma. So in some sense, this is just a non-abelian version of line integral. And this is an invariant observer. This is a gauge invariant. So the whole idea is similar with, in multivariable calculus, if you integrate a vector field along a loop, this integral is invariant if you shift the vector field by gradient. So this is, shifting by gradient is abelian gauge transformation. Okay. What's the difficulty to define this? Because in general, if you look at this measure, the A should be a distribution in general. So in general, so distributions cannot be evaluated at a point, and also in general cannot be integrated along curve. So that's why if you just write the holonomy this way, it's formal. But it turns out that in 2 dimensions, you can make sense of it. So what's special in 2 dimensions? The simplest explanation is the following. In 2 dimensions, say if you look at the plane without any topology, we can always find a gauge transformation of a 2 form A such that the first component is 0. Maybe it's sort of conceivable because the gauge transformation is a function G, right? So now A is a 2-component, 2 functions. Maybe you can use this 1 degree freedom to kill 1 degree freedom here. Right? So, and then of course the second component is not 0. Under such a gauge, if the first component is 0, then now you look at definition of the curvature. So in 2D, the curvature has only 1 component, which is F12. So this is the definition of F12. If A1 is 0, then this is just D1, A2. So this becomes linear, and therefore this energy is quadratic. So essentially the measure is Gaussian. If dimension is higher than 2, this is not true because you can only make the first component to be 0, then you have A2, A3, so you still have nonlinear terms like bracket A2, A3. So such a gauge is called axial gauge. Now, under this gauge, you have a Gaussian measure essentially. Then you can compute many things. So this is why the 2D Yang-Mills measure 2D Yang-Mills theory is an integral model, a solvable model. So one important formula I'm going to use a lot for the rest of today is the driver's formula. So it's from this paper. It says that if you want to compute, right, so in 2D, if you want to compute excitation of some gauge invariant observer, for example, F is just a Wilson loop, or such a loop, then, okay, so this is infinite dimensional integral because it's excitation over the whole Yang-Mills field. But it turns out that this driver's formula tells you that this can be going down to a finite dimensional, actually very low dimensional integral. So how did that? So essentially it boils down to an integral over a few copies of the Lie group. So here E is the set of edges in this graph. So if you look at the graph, there are actually 7 edges. So here is an integral over 7 copies of the Lie group G. And this dq is the product of the Haar measure over the product of 7 Lie groups. What is the density in this integral? Okay, so it's a product of heat kernel on the Lie group. So here the F is a set of faces. For example, in this example, there are 5 faces. So this is just a product of 5 heat kernels on the Lie group. heat kernel has a time and x. So what is the time? So the time here is just the area of this space. And what is the x? So x is a point in the Lie group. So the x here is the holonomy around this space. For example, if the f is the f1 here, then the boundary of f1 has 3 edges. So here this is the product of the 3 q's, right? So every edge is associated with a q variable, with an integral variable q. So here boundary of f1 has 3 edges. So it's a holonomy around f1. It's just a product of the 3 q's. Okay, so this is a very low dimensional integral. I'm not going to prove this driver's formula, but it's sort of reasonable, conceivable, because, you know, if this is just quadratic, essentially you get a white noise or something, and then since the holonomy is defined via this ODE, essentially you get some sort of SD driven by a Gaussian white noise. And then you can, you know, since you have this Gaussian structure, naturally you have some heat kernel. Maybe an example, suppose L is just a simple loop, it's just a circle, say, then excitation of the Wilson loop around this circle is simply an integral over a Lie group. So, right, so a circle has only one edge, so it's integral over one copy of G. And trace Q is a definition of a Wilson loop. And there's only one heat kernel because it's a simple loop, only one phase. And the area is just the area enclosed by the circle. And you just, you know, this expectation of a Wilson loop for a circle is a very simple integral. Okay. And it turns out that you can even integrate all of this. The integral of this is just equal to e to the minus area over 2. Roughly speaking, how do you do this? Well, you know, essentially you need some knowledge about the Fourier spectral analysis on Lie group. You know, if the Lie group is U1, this is the standard Fourier expansion, right? So standard Fourier expansion for you know, heat kernel is like e to the minus t blah blah, and this sort of Fourier analysis also holds on general Lie group. Generally, it turns out that this trace of Q is just one of the Fourier-based vectors. So in general, the trace of any so basically trace of this fundamental representation is one of the Fourier-based vectors. So essentially, this integral is like projecting this heat kernel onto this base vector. So essentially, that's why you get in the Fourier spaces e to the minus t something. That's why you get e to the minus t. So here t is the area. So you can in many cases you can, you know, even for more complicated Wilson loops, you can explicitly integrate out this integral. So this is what I mean by a solvable model. So first step, you can write this infinite dimensional excitation as a finite dimensional integral, and the second step you can explicitly integrate out. Okay. Some remarks. Yeah. So there are also alternative viewpoints of 2D Yang-Mills. It's a solvable structure. For example, perspective by Thierry Levy is that actually you can also understand the continuum limit by so-called consistency over subdivision graphs. Basically, it means if you start with a graph like this. Right? Then you subdivide this graph, make it a finer graph. And then the projection of the Yang-Mills measure on the finer graph to the coarse graph is the same as the Yang-Mills measure on the coarse graph. So in this way, you get sort of projective system. You can get a projective limit as a continuum limit. Essentially, this sort of consistency or consistent of subdivisions because of the heat kernel has the semi-group property. Okay. And then Wilson loops are just observables of A, right? So marginals of A. So what about the A? So actually there's a nice paper by Ilya Chatterjee. It showed that there's a normal gauge fixing, not axial gauge. It's sort of combination of axial gauge with Coulomb gauge. And there's such a gauge that the A actually has optimal regularity. So here, by optimal regularity, I mean, if you look at axial gauge, so if this is like white noise, then maybe the white noise regularity is not it's lower than the Gaussian free field regularity, but you wish that in 2D the regularity Yang-Mills measure should be the same as Gaussian free field. Actually, we show that it's true. So under a normal gauge, indeed A is a random field in this space. And also the holonomy of this random field coincide with the notion of holonomy named before. Okay. So these are the 2D integrable structure. And now what is a loop equation? What is a Makeenko-Migdal equation? In physics, they first heuristically sort of predict that there should be some recursions for Wilson loops. This paper, I think, is not just non-rigorous. It's not very clear that if they really wrote down the complete equation. But then later in another physics paper, they precisely formulate the Makeenko-Migdal equation in 2D, the continuum. Then in mathematics, on the d-dimensional lattice, the Makeenko-Migdal equation was rigorously formulated and derived by Chatterjee first, by Stein's method, or it's essentially integration by parts method. And later there was some alternative derivations. And then in 2D continuum, it was first proved by Levy, and then also later by many other people who reproved this loop equation. So maybe the historical order was actually the 2D continuum equation was first proved, and after Levy's paper, Chatterjee derived the lattice equation. So what is this equation on so let's start from the lattice case. So this is the version of the lattice loop equation proved by Cao-Park-Sheffield. Here, the left-hand side, I have expectation of Wilson loop, L. Now, recall that this Wilson loop is defined by product of the Q variables over all the edges along the loop. I fix one edge, one bound in the loop called E. Now, for example, this UN group, then the equation says that you can write expectation of Wilson loop in terms of linear combination of some other Wilson loops. Okay. So what are the other Wilson loops? These are some sort of deformation or some sort of splitting of the L, some sort of operations of L. Okay. So the first two terms, these are called the deformation terms. What is deformation of L at E? Well, for example, if L is a rectangle, then I can deform a rectangle at E. There are 2D, there are 4 types of deformations. You can deform interway or outerway, right? You can also you can deform in this way, but you can also say, well, I go to the E, but I turn around the plaquette and then go again. So in this way, E is passed twice. So for some weird reason, these two are called positive. These two are called negative deformations. These two are called positive deformations. That's because in the equation they have maybe positive or negative signs. Okay. So this D is just a set of all the deformed loops for L. And then the splitting terms means that, okay, so if L is a rectangle, it doesn't have a self-intersection, then there's no splitting. But if L, say in this picture, the L passes the edge E twice. So in some sense, this loop self-intersects at this edge. Then you can split this loop into 2 loops, right? So here, this is the whole loop, like a figure 8 maybe, but then the figure 8 is split into 2 circles. Okay. So then the L is split into L1 prime, L2 prime, and that's what I mean by splitting. So SL contains all the splitting of L's. In this equation, I have a shorthand notation. Maybe it's not a good notation, but WL prime is actually WL1 prime, WL2 prime, where these are the 2 split loops. Okay, so also something called a positive splitting, negative splitting, just because they come with different signs in the equation. And yeah, so the difference is just we pass the E twice or pass the E and the E inverse. Actually, in the first paper by Chatterjee, the right-hand side is also summed over all the edges E on the loop L. And then Cao-Park-Sheffield proved that this equation actually holds for fixed E. So it's stronger than Chatterjee's original version. Okay. So in some sense, the integration by parts, in the simplest integration by parts for Gaussian measure, it tells you that all the higher moments can be written as a second moment, right? So moments are related. Here is the same, like the moments of the expected correlations of those loops are related with some other loop, other loops. So this is sort of Dyson-Schwinger philosophy. Okay. Now, what is the equation in continuum in 2D? The simplest case is that L doesn't have a self-intersection. In this case, it just says that the derivative of the Wilson loop excitation with respect to the area enclosed by this simple loop is given by -1/2 times the excitation itself. Okay. In particular, from this equation, you immediately get the excitation equal to e to the minus area over 2. That's consistent with what we get from the reverse integral formula. Now, more interesting is L has an intersection at V. So imagine this is the whole loop, but I only look at the neighborhood of this loop around the V. So this is how the neighborhood look like, right? So there are 4 edges. So this whole loop is like you start from V, you go out through the E1 and then do something else, come back through the E4, and then go out from E2 again and do something else, and come back from E3. That's the loop. And the master loop, the Makeenko-Migdal equation says that the alternative area derivative of this Wilson loop excitation is equal to the excitation of the product of 2 loops, and L1, L2 are splitting of L. So how do you split? So basically L1 is this part. So L1 is basically you start from V, go out through E1, do something else, come back to E4, then stop there. So this part is E1, and the other part is E2. Okay, so it's again like figure 8 split into 2 circles. Okay. Maybe I should mention that these loop equations are not only of theoretical importance, but also extremely useful. On the lattice, Chatterjee, for example, Chatterjee used them to establish a sort of gauge string duality. Which means that one can represent the Wilson loop correlations as a sum over surfaces. Okay, so similar as like in spin models, you can write correlations and random walk sums or something. So this connects to the theme of this workshop with random geometry. So this sort of sum over surfaces is kind of discrete analog of random surfaces. Another paper by Su and Crescendo, they used the Chatterjee's loop equation to study the area law. For example, it's very interesting result that they find an example Wilson loop which actually decay faster than the area law. So in some sense, the area law lower bound is not necessarily true. They basically use the loop equation and do some combinatorics and so on. One can also use the loop equation on lattice or continuum to study large n limits. I believe Levy had a result like this. And you can also use the loop equation to exactly calculate many Wilson loops. I showed you the example of the circle, right? You can of course do like figure 8 or some complicated loops. You can try to exactly calculate using such recursions. Because, for example, if you start with a complicated Wilson loop, then you can use this use this sort of equation to split at the intersecting point. And after many splitting and so on, after you sort of use this equation for several times, maybe you end up with a much simpler loop, like a circle or something. Then you can solve it. Okay, these are the many applications. Yeah, some examples of many applications. Our question about half of the talk. So now our result, we want to show convergence to continuum. So in terms of convergence to the Young-Mills, there are a few types of convergences. So even back to driver, they know that in 2D, if you sort of do a lattice approximation for a loop, so given a loop L in continuum, and then L epsilon is sort of zigzag approximations, then they know that this Wilson loop expectation converges to continuum. So you have convergence of Wilson loops. And then how about on the level of the connections? We also know that the measure on the space of connections modulo gauge transformations also converge. Actually, this recent paper with Ilya, we proved this result actually by showing the convergence of the stochastic dynamic, the stochastic quantization. So since this measure is an invariant measure, once we show the convergence of the SPDE, then we can argue the convergence of the invariant measure. So I guess initially Makeenko-Migdal called the loop equation as equation motion, quantum equation of motion. Usually in quantum field theory they call this Dyson-Schwinger quantum equation of motion. So now our question is convergence at this level. So actually this is one of the many proofs for the loop equation of the plane. In the paper they remarked that Chatterjee has a rigorous version of Makeenko-Migdal equation on the lattice, and this equation takes somewhat different form from the continuum loop equation. And you can obviously see that the two equations are very different, and that's the difficulty. So in particular, you see here in the discrete loop equation, you need to fix an edge on the loop, but you don't see this at all in the continuum, and I guess in some sense, okay, so the similarity is that here we have a splitting term, here we also have splitting at an edge. And here the deformation heuristically is sort of infinitesimal area derivative, right? Deformation is like you change the area enclosed by the loop a little bit, but still hard to really show how this can convert to that. Okay. So the question is the converge in what sense, and also what edge E you should choose in this equation to converge to this, or you need to maybe choose several edges along the loop and combine them or something. And if there are any cancellations between these terms.
So I have a question.
Yeah.
So in the continuum, is it only of interest to look at loops with finite intersections, or is this slightly more complicated with the?
You can certainly have a finite, many intersections, and also each intersection you not necessarily 4 edges going out. You can have many edges.
So your results will cover all of that.
Yeah. Okay. So maybe I can illustrate our main techniques using the simple loop. Because now we don't have splitting. So, so suppose L is a rectangle, then we have 4 deformations at E. So lemma, it turns out that somehow, okay, you see there are 2, so basically it turns out that these 2 deformations cancel. So these 2 deformations, we call them outer deformations. Not just cancel in the limit, they actually cancel for each fixed epsilon, where epsilon is the lattice space. This was special in 2D. I don't know if this is true for higher dimension. And so we only need to look at the 2 inner deformations. And in equation, they come with different signs, 1 plus, 1 minus. And the lemma says that 2 inner deformations combined together, we need to make use of the negative sign. They combine together, converge to the area derivative of the Wilson loop. Since we also know, back to driver, that the left-hand side converge to the continuum limit, then we just get the area derivative is equal to the left-hand side, which is the E of W. So this is exactly the continuum loop equation. Okay. So I don't have time to prove both lemmas. The second one is more interesting, so let's look at the second one. The idea is that since maybe I forgot to say that in continuum we have a driver formula, right? You can compute these expectations by finite dimensional integrals. But on the lattice, there's also a driver formula. So on lattice, right? Oh, I see. So on the lattice, the Wilson loop expectation also satisfies driver's integral formula, except that the heat kernel in the formula should be replaced by a random walk density, a transition property to random walk. So that's the only difference. So the idea is that now we just use the driver's formula on lattice to calculate these each of these deformations and put them together and see what's the limit. Okay, so first of all, what is the random walk, right? I mentioned there's a transition probability random walk in the driver formula. Recall that our lattice Young-Mills model was defined by the so-called Wilson model was like a trace of real part of trace identity minus the Q. We just think of this e to this distance between I and Q as the transition probability of random walk on the Lie group. So the random walk which goes from identity to Q. Okay, normalized. So I call this transition probability S. Discrete driver formula says that this deformation, this Wilson loop excitation is equal to integral over again the Lie group, right? So now only one face. Sorry, only one edge, which is the entire edge. So I only have one Lie group here. This is the Wilson loop, the trace of Q. And now this is the random walk probability. So how many steps of random walk do I have? Basically, so the T here is the area enclosed by this loop. Now, okay, so the T is the area of the rectangle, but this is deformed rectangle, so it's T minus epsilon squared. The epsilon squared is the area of this plaquette. And divided by epsilon squared, basically, I'm counting how many plaquettes in this deformed loop, and that's the number of steps this random walks take. Okay, so this is the discrete drivers formula. Now, remember that I want to show that these two deformations combined together goes to the area derivative. For this one, I can also use the driver formula, but now there are, okay, I have to think of in this picture, I have 3 edges, which is I go along the red edge, E1, goes down to the Q1, and at E, I pass E first, and then I go to E2, and then I pass E again and go back. Right? So E2 corresponds to this blue variable, and E is this variable. So now I have 2 faces. There's this whole big face and this little plaquette. That's why I have 2 copies of transition probability. Okay. Now how to compare them? One trick we always use is remember gauge fixing. So in 2D there's actual gauge fix. You can make one direction to be 0. On the lattice, the analog is that you can take a tree in the lattice, and then you can see on the tree all the Q variables are identity. In particular, you can take the tree to be one horizontal line and all the vertical lines. This corresponds to taking that direction, so that the first component of the A1 form on that direction is 0. So because of this very nice gauge fixing, you can actually feel free to choose a tree in the picture, and you just say on the tree it's just identity. For example, we can say we can just take the E, one single edge, to be a tree. Right? One single edge is a tree, so you just say, oh, the Q at E is just identity, and just erase the Q. So the triple integral becomes a double integral. So it's now only Q1, Q2, which corresponds to the red line and the blue line. Now I want to compare this with that. Of course, here you see here this key kernel, this transition probability and this transition probability is essentially the same, except Q to Q, Q1, Q2 inverse. So I just do a change of variable. So I just call this whole thing a new Q, and I still wanted the Q2, but the Q1 can be written as the Q and the Q2. So here I don't have Q1, but I have something else. Just a change of variable. What's nice is now this looks closer to that. Well, I also have Q2, but here you can just add a Q2 for free because the integral of SQ2 is 1, because S is a random walk probability. Right? So you can just take another integral over S of Q2 here without changing this. Now the only difference is that this is the trace of Q, this is a trace of Q2 inverse, Q2 squared. So it's just boiled down to understanding the difference between between trace of Q and trace of Q2 squared, because the heat kernels are actually the same. Okay. So how to do this? How does the area derivative pop up? So this okay. Again, I just summarize the difference between the 2 deformations. I get this trace of the difference. Now we need some analysis, some asymptotic analysis. So this says that if you integrate some function against the random walk transition probability, so this random walk can only take one very small step. So it's still very close to the identity. If epsilon is just 0, then it's actually just the delta function at the identity, then this just gives you the f at the identity. But for a positive epsilon, essentially, well, this S of Q looks like it's still very close to identity, so you can turn the problem to the Lie algebra, the tangent plane identity. And on the Lie algebra is approximately the Gaussian. So after some error, we need to control essentially this integral of FQ against some Gaussian. That's why we have the second term here. Or you can also think of the other way is you can pretend S to be e to the epsilon squared times Laplacian, right? So heat kernel basically e to the Laplacian. When you expand that, you also get a Laplacian. Okay, so this sort of asymptotic terms ought to be useful, because here you see here this S of Q2 is just a one-step transition probability of random walk. So you can use this asymptotic formula to integrate out the Q2. Right? So I think of this function as the f there, so f is a function of Q2, and I get this. So that's why the Laplacian arises. So once I have a Laplacian, so Q2 is already integrated out, but I still have the Q2. And then I can integrate by part and put the Laplacian on the heat kernel. And since the heat kernel Laplacian is equal to the time derivative, and what is the time? Time is just the area. So this is exactly the driver formula I showed you earlier for a simple loop. Right, so this is how the two deformations combine to give an area derivative. Okay. Okay, so that's the simplest case, just to illustrate the idea. And with self-interaction, it's much more complicated. So this is the neighborhood of the self-intersecting point V. It's adjacent to four edges. So we take a lattice approximation. We should require, okay, we can do a large class of lattice approximation, except that we have to assume that the intersection is approximated by a few edges. Otherwise, we don't have a splitting term in the lattice equation. Okay, so now I want to show this with deformation and the splitting term go to continuum limit. The first question is, what is the little bound edge I should choose here, right? So I said the lattice loop equation holds for any choices of E, right? You can choose E to be any bound on this discrete loop, this hole. So the question is, what is the E you should choose to get this limit? One natural guess is, since you want the splitting term, you should choose a bound here in the middle. That's a natural guess. So if you apply the discrete Makeenko-Migdal for a bound in the middle, so if you choose this bound, then you get all the deformations, right? These are all the deformations. And then you also get a splitting term. And then by many calculations, you fix a suitable gauge, you do some spectral theory on the Lie group, and some asymptotic analysis, some Gaussian formation, and so on, so on. It turns out that the limit goes to the combination of all the terms on the right-hand side of the discrete loop equation. The combination converts to this equation with some undesired terms. So first of all, this E of W shouldn't be there, shouldn't be in the continuum equation. And there's also some weird term called J. I don't want to write, but J is also shouldn't be there. So it turns out that the right idea is that we shouldn't only take a bound in the middle. We should also take a bound maybe here and also there, and then combine, right? So basically, you should use the discrete Makeenko-Migdal equation for a bound in the middle, and also a bound there and there maybe. So and then combine them to get the right continuum limit. So that's what we do. So we actually take another bound here and here, then we apply the discrete Makeenko-Migdal for these two bounds. So these two Makeenko-Migdal equations convert to these two continuum limit, and they also have, okay, so they're also not the right equation because they don't have splitting term, right? If you take a fixed bound here, of course you don't split. Only take a bound here, you split. So there's no splitting term in the continuum limit, and also there are some undesired terms, J1, J2. But if you combine this equation and these two equations, combine the three equations, it turns out the first equation minus 1/2 second equation minus 1/2 third equation indeed goes to the right continuum limit. So if you do this linear combination, actually all the undesired J terms and also this term actually cancels out. Okay, so now what's the formulation of our theorem, right? So to answer our earlier question, in what sense they converge? Basically, suppose L is a what we call that a self-intersection. Ignore the symbol. Then we can consider a large class of lattice approximations, L epsilon of L. And we also have a general rule of selecting bounds from this discrete loop, right? So the rule is like you can choose some bounds from middle and some bounds outside. There's some rule I'm not going to write down, such that suitable linear combinations of the discrete loop equation with these selected bounds, the linear combination converges to the right continuum. Okay. So this clarifies what sense converge. In particular, in this convergence result, convergence proof, we never use the limiting the continuum loop equation. And therefore, as a corollary, this gives maybe the 7th or 8th proof of the continuum Makeenko-Migdal equation after all these earlier proofs. Maybe Shen asked this question. So suppose the intersection is not adjacent to 4 edges, instead only 2 or more, we can also deal with call it degenerate cases. We also proved so we have some generalizations, like if you not only one loop, but a correlation of m loops. There's also a version of a loop equation we can prove convergence. So there it's not just splitting. Actually, these different loops may merge to form larger loops. So these merging terms appear in both lattice level and continuum level, and they also converge. So to conclude with some questions. So we only did the plane case, but it'd be nice to extend to surfaces. So I believe we can write down lattice loop equation on surface, and there's also a version of a surface continuum loop equation on surface. So, it's a bit strange that such loop equation was never studied with discrete loop. So that would be interesting. So these are probably feasible problems, but much harder question is like the lattice loop equation is holding all dimensions, but so that does it give us some hint about what happens in the continuum when dimension is larger than 2. Of course, the difficulty is that when dimension is larger than 2, we don't have driver formula. So our proof really depends on driver formula. So also, actually, if you couple Young mills on the lattice, you couple Young mills with a matter field such as Higgs. One can also easily derive a loop equation in this case. So it's not just closed loops. You can also look at open Wilson lines, where on the 2 ends you put 2 Higgs fields. It's also gauging environmental observables, so they also satisfy nice recursions. The recursion, the loop may break into an open line may glue back to a loop. Even in 2D, does it give us any hint what the continuum loop equation should look like for Higgs model, for example? More and more, there's integration, talk about integration by parsing random conformal geometry, how to compare it. Okay.